In this lecture, we are going to explain how we could work with the stack. There are two instructions for moving data inside the stack or retrieving data from that, which are push and pop. So in here, I just create a file called, even though in the previous lectures we promised that whenever we are in need of some instruction, we would explain it. But right now, well, because these instructions are so useful, I just want to explain them. But if I want to tell you about the when we need that, you remember that in previous lectures we wanted to implement the functions, and we said we use the return address at R8 register, and then we saw that the call and return instructions themselves, they use push and pop because they want to make the general purpose registers like R8 available to us. So if they want to store a value and then restore it later, we would always use the stack instead of other registers. So in here, if I just want to explain how this stack works, I create a file. Let me just name it stack.nasm in here. First create the global start symbol in here, and then I say section.text. After that, I create the entry point. Then I say section.data if we need this data actually. Now at the start, I want to first push a hexadecimal value of, let's say, 1 2 3 4. Then I want to, well, let me actually pop it first to R8 register. After that, I would want to push the value of, let me create some data in here, mgh hello db, and then hello world and 0xa in here. I want to push the, well, I want to push the mgh hello, which would be the address of this label, to the stack. Also, I want to push the content saved in this address. You would see the difference. Then I want to push a decimal value of 64, let's say. Then I want to pop the value inside the R9 register. I want to again say pop R10 register. Then I want to say again pop maybe R11 register. Now I say Ctrl O to save it, hit enter, Ctrl X, use the NASM and linker to assemble and link it. Well, the operation size not specified in the line 9, 1 2 3 4 5 6 7 8 9. So we should specify that what is the length of what we want to push, because if you pay attention, we have for example, let's say we have 11 bytes or 12 bytes in here, but how many bytes do we want to push in the stack? Do we want to push hello world, hello w, or how many bytes do we want to push onto the stack? Let's say that I want to just push 8 bytes in here, so I say push q word mgh hello, which means that I want to push 8 bytes from the address that mgh hello is pointing to. So it would be at HELLO, which are 5 6 7 and 8. You would have these addresses from here to O pushed onto the stack. Then we would want to push 64, which is a decimal, and you would want to pop every one of them. So I just save it, exit, again assemble it, and now we don't have any error. Now we want to link it. We create the executable, we execute it, and we would definitely have a segmentation fault, as you see in here. And I hope you know the reason. The reason is that we haven't exited from this program. So after all of these instructions have been executed, the RIP would increase. You would get to another address that maybe get executed. You may have good results, and it would go on until we get to an address which we shouldn't have. We don't have the access to. We want to get to an address which we don't have an access to, or some bytes have been decoded as some instruction or other thing that we explain, and therefore we get a segmentation fault. If we create an exit system call in here, we wouldn't get a segmentation fault. So I exit. What I want to do is to enter the GDB to explain every one of these things. So I say GDB and then a stack. I hit enter. I create a breakpoint at the starting point. I run. Now I say also I want to say obj dump -m intel -d and then a stack to see all the instructions in here. If we say info registers and RIP, right now RIP is pointing to 4000B0, which is exactly this address, and we have push 1234, right? Now if we look at the RSP register, which is the register which points to the top of the stack and hit enter, it shows us this address E2C0. Now I copy it and I want to see the contents in here, so I use the X command because this is a memory address. We explained that we could do it using a $sign before RSP and it would show us the content at the stack, but I want to do it in this way. We look at the RSP register, it shows us the memory address in the memory, which happens to be the top of the stack, so we use the X command because we want to see the contents at the memory. I say X /1X. X means that I want the contents to be represented in the hexadecimal, so I say 1X and then let's say for example G, and I paste it in here to see the giant word in here. So I hit enter and we see this value in here. If I wanted to see only 1 byte, I would provide the B. If I hit enter, I have 0, 1, which means that nothing has been pushed by us. So I say step I. Now I look at the RSP again. So when I said step I, this has been executed. Something has been pushed onto the stack. If I say RSP, if you look, we have E2B8, which means that the stack has grown. If you look, the last top of the stack was E2C0, but it is B8. So if we open a calculator in here and look at these addresses again from C0 to B8, right? So if I say int and C0 and 16 and hit enter, we have 192. If I say B8, we have 184. 192 minus 184, we have 8, which means that B8 in here, this address is 8 bytes lower than E2C0, which makes sense because we said that the stack would grow towards the lower addresses. So because right now we are at E2B8, which means that the stack has grown by 8 bytes, right? And actually by default in 64-bit architectures, the push command would increase the size of the stack by 8 bytes, while in 32-bit architectures the push would increase the size of the stack by 4 bytes. So now if I want to see the content in here, I could just copy this value. This would be the top of the stack, say x1xg for example, paste it and hit enter, and if you look, we have 1 2 3 4 in here and all of these zeros which have been pushed into the stack. Now after that, we want to look at other instruction, which means pop R8. Pop R8 means that pop this value into the R8 register. So I say step I, and now if we look at the RSP register, now it shows the first address E2C0 in here, which means that the stack length has been decreased. If I say info registers R8, now you see that we have 1 2 3 4 inside the R8 register. So because we wanted to move something to R8 register, let's say we first pushed it onto the stack and then pop it inside the R8 register. The stack length has been increased and then decreased to its original size. After that, we say push mgh hello, which is at this address. So by saying this actually means that we want to push the address inside the stack. So again, I say step I have a look at the RSP register. It points to this address. I have a look again at this address in here. It shows us the memory address of the mgh hello. Now if I step I again, now if you look, it's push keyword at mgh hello. If you look at the assembled or when it has been assembled, well, the labels have been translated, right? So in here, if you look, it says the assembler have translated the label to address. It says push keyword, push 8 bytes from the pointer which points to this address. So we want the contents at this address from 8 bytes later to be pushed onto the stack. Therefore, I say step I, and if we look at the RSP, we expect that this the RSP would be 8 bytes lower than this address. If I hit enter, you see that we have E2B0, which is exactly 8 bytes lower than B8, which means that the stack has grown by 8 bytes. Now, if you want to look at this address in the memory, the contents at in here, so I say B0 and hit enter, you see that we have this value. Let me actually make sure that this is hello WO. So I just copy it. You could use any calculator that you want. I go to the Python, import bin ASCII, hit enter, bin ASCII.unhexlify, paste it in here and hit enter. Well, it tells us odd length string. Let me add a 00 in here. Let me see the problem. Well, I think I haven't just get the whole string. Let me just copy this value, or actually I have it. Let me just say len and then paste it in here. I think I haven't copied the whole of it. Now if I hit enter, we have, yes, we have 15. I should copy all of it, so 6f to 68 in here. Let me first make sure by giving it to the len function, which gives me the length of the all of the string. Now we have 16, yes. So I say to go to the bin ASCII on hexlify, I paste it in here, hit enter, and we have OW, OLLEH, which means hello, and WO, which is the same thing that we expected in here. We said 8 bytes, we only get 8 bytes. So after that we get to push 0x4t, because if you look, we want to push the decimal of 64, which is equivalent to 0x4t in the hexadecimal. Therefore I say step I have a look at RSP. It has been again grown into A8, and therefore another 8 bytes have been added to the stack. After that we have to, actually let me just show the contents at this value in here. So I say copy or E2A8, hit enter. This is the new value that we have in here. After that we pop the, now in here is important, we have 3 pops, right? When we say pop R9, the first word would be popped inside the R9 register. Right now at the top of the stack we have these 40 hexadecimal, right? So if I say info registers and then R9 register, I don't have anything in it. Now if I say step I and hit enter and have a look at R9 register, we have 64 in decimal or 0x40 in hexadecimal representation. If I have a look at the RSP register, now the top of a stack is E2B0, and if we look at this top of the stack in here, B0, now we have this hello world, which means that we don't have the 64 at the top of a stack anymore. Or actually we have it, but it could be overwritten. Now after that we want to pop the next value at the top of the stack, which is this value inside the R10 register. So if I say info registers and R10, we don't have anything. If I say step I and then R10 register, now we have this value inside the R10 register. And again, if you have a look at the RSP, now it has been decreased again. If you have a look at this new address, would be 6000 cc, which is this value in here, this value in here. So as you see, the last in first out have been shown to you in this way. Now if I say the next register is R11, right? So if I say R11 in here, we don't have anything in it. If I say a step I and have a look inside the R11 register, we would have 6000 CC inside the R11 register. Now the RIP register would be pointing to 4000 CB. 4000 CB, well, we don't have anything inside that, because at 4000 C9, well, the 2 bytes in here would be added to the RIP current value, which was 4000 C9. Now we have 4000 C11. If you have a look at 1xg 0x 4000 and C9 and hit enter, you saw that we had this address at 4000 C9, right? Which if you look, it's 415B in here, which 415B is equivalent to pop R11. So the CPU would look at these 2 bytes, it decodes them, sees them as pop R11. But if we look at the C, now in here would be CB, which is 2 bytes after that, and hit enter, we have, for example, 0068, which are some garbage values. The CPU might decode them as another instruction, or maybe it wants to jump to some inaccessible memory address, and it would give us some segmentation fault, which would be the reason of what we saw in here.